Today we're going to be talking about how to determine whether two planes are parallel or perpendicular to one another, or if they're neither parallel nor perpendicular to each other, how to find the angle between the planes. And in this particular problem, we've been given the equation of two planes. One is x plus 4y minus 3z equals 1. The other is negative 3x plus 6y plus 7z equals 0. So the easiest way to go about this is to test for first parallel, then if not parallel, perpendicular, then if not perpendicular, to find the angle between the planes. So we want to test for parallel first. What we need to remember about finding the angle between planes and deciding whether or not they're parallel or perpendicular is that we can use the normal vector of each of these planes to conduct the same exercise. So as opposed to figuring out whether or not the planes themselves are parallel, what we know is that if the two planes are parallel to each other, their normal vectors are also parallel. Remember that the normal vector is the vector which is perpendicular to the plane. So just as a quick illustration here, and I'm not going to draw this very well, but if I'm looking at the edge of one plane and I have a plane here, I'm looking at the edge of it and it's going back behind this plane, and then I have another plane over here which is parallel to it, and I'm looking at the edge of each of these planes. They're going back into space. If these two planes are parallel, their normal vectors look like this. I have the normal vector of this plane coming out perpendicular from the plane, and then the normal vector of this plane coming out like this. The normal vectors are going to be parallel to one another. So it's easier for me to test to see whether the normal vectors are parallel than it is to test directly whether the planes are parallel. So what I want to do is find the representation of the normal vector of each of these planes and then see whether those are parallel or not. So to find the normal vector, all I need to do is take the coefficients on each of my x, y, and z terms in each equation of the plane. That'll give me the components of my normal vector. So for example, the coefficient on this x term here is just 1, right? I have 1x, there's this kind of hidden 1 here. I have 4 in front of my y, so I've got 4 here, and I've got a negative 3 in front of z. So the representation of my normal vector to this plane is 1, 4, negative 3. That's the normal vector to that plane. Same thing over here. I take the coefficients. My normal vector is negative 3, 6, 7, like that. So now that I have a normal vector for each one, the way that I can test to see whether or not they're parallel is by taking the ratio of each of my components to see whether or not the ratios are equal. Here's what we mean. I have my x component for my first normal vector here, it's 1. I have the x component in my other vector, my other normal vector, that's negative 3. I want to take the ratio of those two, so I'm going to say 1 divided by negative 3. I want to set that equal to the ratio of my y components and the ratio of my z components. So I'm going to do 4 over 6 and negative 3 over 7. I've got my x components, y components, and z components. If this equation is true, then I know that my normal vectors are parallel, and therefore by the logic we talked about before, I know also that my planes are parallel to one another. If this equation is not true, I can conclude that my planes are not parallel because my normal vectors are not parallel. Well, as we can see here, even if we reduce this here to 2/3, this equation is not true. 2/3 is not equal to negative 1/3, and neither of those are equal to negative 3 over 7. So I know that my normal vectors are not parallel, which tells me that my planes are not parallel. So I can go ahead over here and say not parallel. I know my planes aren't parallel, so now I need to test to see whether or not they're perpendicular. Well, the same logic follows if I have perpendicular planes, and let's pretend that we're looking again at the edge of our planes. So I have two planes like this, which are perpendicular. If I think about my normal vectors, I have the normal vector to this plane going this way. I have the normal vector to this plane going this way. You can see my normal vectors are going to be perpendicular as well. So what I really want to test for is whether or not my normal vectors are perpendicular. If they are perpendicular, I can conclude that my planes are also perpendicular. The way that we test for vectors being perpendicular to one another is to take the dot product of the vectors. So I have my two vectors, 1, 4, negative 3, and negative 3, 6, 7, and I want to take the dot product. So let's pretend that this vector here is A and that this vector is B. I'll call my dot product the dot product of A and B. And remember, to take the dot product, we just want to multiply our components. So again, our x components are 1 and -3. I want to take the product of 1 and -3 and add to that the product of my y components, 4 and 6, and then add to that the product of my z components, -3 and 7. When I simplify this, I get -3 plus 24 minus 21, and I can see here that this is equal to 0. That's exactly what I want. If my dot product is equal to 0, then I know that my vectors are perpendicular to one another. So I've proven that my normal vectors are perpendicular, which tells me that my planes are also perpendicular to one another. So perpendicular is then going to be my final answer for this problem. However, I want to walk through this with you guys. What if my result here had not been 0? If the result of my dot product is a non-zero number, I can conclude that my vectors are not perpendicular to one another, which tells me that my planes are not perpendicular. If my planes are not parallel and they're not perpendicular, then I know that there's some angle between the planes. How do I find the angle between the planes? Well, in that case, I use this corollary formula: cosine of theta is equal to the dot product of A and B divided by the magnitude of A times the magnitude of B, or really what we're saying here, the length of our vector A times the length of our vector B. So I'll walk through this formula with you guys. It won't make sense using these numbers because we know that our vectors are perpendicular. But if I wanted to use this, here's what I do. I'd say cosine of theta is going to be equal to the dot product of A and B, which I already found here. So it's 0. Let's say I had a non-zero number. I'd put that in, but here I'm going to put in 0 just to stick with the same numbers. So I'm going to put 0 in my numerator, divided by the magnitude of A, or the length of A. Well, how do I find the length of A? I use the distance formula for 3 variables, and here's what that looks like. It's really just the square root. When I have it in vector form here, it's the square root of each of these direction numbers squared, and then I take the sum. So what that looks like is 1 squared plus 4 squared, my y component, and then -3 squared. So plus -3 squared, like this. This value here is going to give me the length of A. Then I want to multiply that by the length of B. So again, I take -3 squared plus 6 squared plus 7 squared, like this. And of course, I keep it all here in the denominator. So I'd come up here with some value. In this case, I'd have 0 divided by the square root of 26 times the square root of 94. That's how those square roots simplify. And I could calculate this on my calculator. But if you're trying to find the angle between the planes because you concluded that your planes were not parallel and that they were not perpendicular, you get to this point, here's what's important. Make sure your calculator is set to degree mode, not radian mode. Normally, you should have your calculator in radian mode, but in this particular case, when you're looking to find the angle between planes, you want to make sure you have your calculator in degree mode. When you do that, here's how you're going to solve this for theta. You're going to take the inverse cosine function, or cosine of the -1, or arc cosine of both sides. When you do that, you're going to get cosine over here on the left to cancel, leaving you just with theta. That's going to be your angle between the planes. So you're going to get theta is equal to arc cosine, or cosine to the -1, of your value over here on the right. In our case, it's 0 over square root 26, square root 94. This 0 right here again tells us that our planes are perpendicular, which we already found when we took our dot product. But in your case, if you had gotten a non-zero answer, you're going to have a non-zero number right here. You're going to take arc cosine, or the inverse cosine function of some non-zero number, divided by whatever square roots you end up with here in your denominator. That's going to give you a value for theta. And again, just make sure your calculator is set to degree mode. Whatever answer you get here will be the angle between the planes. So that's how you can use the normal vectors here, which we found A and B, to determine whether or not two planes are parallel or perpendicular, or if they're neither parallel nor perpendicular, to find the angle between the planes.